All right, let's talk a little bit about direction cosines. This is a very important concept that is used in transformations of physical objects that are rotating in space. Think like an airplane. If you're an airplane, you're always looking down your nose. But even when you do a bank, you're still looking forward, but your body's rotating in space. So this idea of direction cosines are used all over the place to kind of understand that orientation, or attitude is sometimes the term that's used. But anyway, in 2D space, it's pretty simple to think about the angle that a vector u forms with the positive x-axis, right? We can think about it's rotated up, and if we want to find that angle, we simply use what we already know about the dot product and say, let's take u dotted with the the standard vector I. So if we do u dot I, and then we divide it by the magnitude of u and the magnitude of I, well, what we get is this simplified u1 over the magnitude of u. And that happens because the magnitude of I is equal to 1. And since I is 1, 0, when you dot it, the second component disappears and you're only left with the first component. So cosine of theta is equal to u1 over its magnitude. So that's fairly straightforward in 2D. But if we move over to 3D, we have this jumble. We can't just do it with two angles. That's not enough. If we want to think about that attitude, we need three angles. At least if we want to do it from the axes. Anyway, there's a way to do it without that. But we can use those standard vectors, I, J, and K, to develop three different angles. We're going to call them alpha, beta, and gamma. We're not going to use theta because we've already talked about using theta and phi and stuff when we've talked about, or rather we're going to get to that when we talk about this idea of rectangular and cylindrical coordinates. It's not rectangular, spherical and cylindrical coordinates. And we don't want to confuse those angles with these angles. So we're going to use this alpha, beta, and gamma to represent the offsets from the positive x-axis, the positive y-axis, and the positive z-axis, respectively. And we call these angles direction angles. And they have a similar relationship. Notice that cosine of theta in 2D was u1 over the magnitude of u. Well, it's the same idea. For the positive x-axis, we still have that relationship. But now for the positive y-axis, we have this relationship. And the positive z-axis, we have this relationship. So if we moved all that back together and thought about the way that u is constructed, what you get is that u is equal to this times I plus this times j plus this times k. And if you think about it, that's actually really neat, because if you thought about the way we had to do it before, we had those polar coordinate relationships, there was a sine component and there was a cosine component. But in this case, we only need those cosine angles and that magnitude to determine the way a vector should be. We also have this relationship, and that follows directly. If you took the magnitude of all of this and scaled out that magnitude of u and blah, 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 this falls directly from this. So, feel free to do that as an exercise. But ultimately, direction angles, we're covering this not because it's necessary for what we're going to be doing mathematically, but it's a very, very important concept in the way that a lot of simulations, a lot of physical representations of physical phenomena are represented. This is very, very common. So it's important that you look at it, you're familiar with it when you engage the real world.